Okay. Hello everybody, welcome to this afternoon session. So our first speaker is Caroline Davis from Indiana University, and she's going to talk about marked cycle curves.
Thank you. So yeah, on the program it said I was going to give you, was it not on? Okay. Now it works? Okay, cool. So on the program it said I was going to give you a tour of Pern curves. And I really do love the Pern curves, the Pern zero curves. But I didn't want to just be some random American coming down to the Italian-Brazilian conference. And so I wanted to talk about some joint work that I have with someone who is Italian, Giulio Tiozzo, who couldn't be here. So that's my connection, I guess. There'll be another Italian connection later in the talk as well. But basically, a lot of math that we've seen so far in the week. So basically, the only goal, well, two goals. One is that we have a good time. That's on you. Okay, two is I just kind of want to explain some of these pictures that we've been thinking about over the last couple of years, okay? And before I get into it, I kind of want to say that these pictures remind me of like a riddle that I heard when I was a kid, you know? So the riddle goes, and I'll translate it to Brazilian currency, I guess, is that I have two bills whose value adds to 22 real, okay? So I have two bills that add to 22 real, but one of them isn't a 20 bill. So what are my bills? Okay, so there's three ways you can answer this problem. One is just, oh, it's impossible. Second one is you can say, oh, well, I looked in this historical almanac, and there's this really important guy from 100 years ago who owned a $10 real bill, but now after inflation or whatever, it's worth like 20, so that plus a normal 2 is equal to 22. But the real way that you answer it is you say, one of them isn't a 20, but the other one is a 20, okay? So that's kind of the motivating principle behind looking at a marked cycle curve, is that is illustrating that there's like a marked $20 bill. One of them isn't a 20, but the marked one is a 20. Okay, and my claim is that that riddle has something to do with these fractals that we're seeing right here. So what are these fractals that they're living in? Well, these are all living within families of rational maps. And if you wanted to enumerate every possible rational map, well, that's a little hard. Let's just focus on degree d equals 2. At the end, I can tell you what generalizes pretty trivially to higher degree. But at least for d equals 2, you can write a rational map as a ratio of two quadratic polynomials. Each quadratic polynomial has 3 coefficients. You have 3 coefficients on top, 3 coefficients on bottom. But secretly, you know, there's a ratio to them that if you just multiply it by some constant, it's not really changing the rational map. So you really have a 5 complex dimensional space of all of your quadratic rational maps. But these are acting on the Riemann sphere, and the Riemann sphere has automorphisms to it. These are your Mobius transformations. And we really don't want to look at something that's too much in coordinates, because when we look too much in the coordinates, we're losing about what's the underlying combinatorial properties to our maps. So doing that, the sort of moduli space of all possible quadratic rational maps is this little ret 2, which is all of our rational maps that are modded out by conjugations by our automorphisms. And this is a 2 complex dimensional space because 5 minus 3 last time I checked was equal to 3. Sorry, 2. And there's a lot of spaces that live inside of here. The 2 ones that I want to talk about today, well, I might not have time to talk about the second one, but we're definitely going to talk about the first one, which is this. Does anyone recognize this shape? Anyone? Yeah, that's right. It's the Mandelbrot set. But the point is that the Mandelbrot set is the fractal. The whole underlying space is the space of all quadratic polynomials, z squared plus c. The Mandelbrot set is the fractal that lives inside of this parameter space that has a certain connected Julia set condition, right? And this is looking at polynomials, and every polynomial has infinity. That's a critical fixed point. But then you can also look at rational maps that we'll look at the end that have not a critical fixed point, but a critical 2 cycle. And then in there, if you draw the parameter space, there's something that kind of looks like the Mandelbrot set in there. I'll make this more precise later. But then inside of it, there's also, again, the curve PR20, the parameter space is the whole plane, but then there's like a Mandelbrot set analog inside of there. Before I go on, I've been studying complex dynamics for long enough, and if any of you have any complex dynamicist friends, you know that they'll say like weird things like the Cocopelli tuned with the Cocopelli is like blah, 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 you know? It's like we give these things like random weird names or whatever, and unfortunately, I will be saying those things. You know, it's like I couldn't not if I tried. So just to translate, when you look at the Mandelbrot set, there's this big main component, right? And this one contains the map z squared in it, so its Julia set is just a circle. But then some of these other components that have, so I guess what I should define by hyperbolic component is that if you look in the Mandelbrot set, you see all of these different disks that are labeled by different colors. And these are parameterizing open regions such that the number of attracting periodic cycles are the same numbered inside of each one of those bulbs. So everything inside of this big blue region has an attracting fixed point, which means that the derivative at your fixed point is less than 1 in modulus. But as you understand, there's a whole disk's worth of numbers that are less than 1, right? You can have 1/2, you can have 1/4, you can have 1/2 plus 1/2 I. And this is this multiplier function that gives us a parameterization on our disk that tells us that for every parameter, you can have having an attracting fixed point that has a derivative equal to that number in the disk, and that's called the multiplier. This multiplier is well defined on a periodic cycle. So if you look, for instance, at this purple component, this is parameterizing all of your polynomials that have an attracting 2 cycle. The center of it is when it's derivative 0 and it's a critical 2 cycle. But if you had the 2 cycle that has derivative 1/2 on it, then this is also having this multiplier function right here. And I wanted to spell this out, is that this 2 cycles, we call the guy inside of here the basilica. Inside of the 3 cycles, we have 3 cycles. One of them is the rabbit. Some people think the fractal kind of looks like a rabbit, I guess. And then the one that's complex conjugate symmetric to it is called the co-rabbit. Then over here, we have the airplane. And then the 4 cycles, this is a 3 cycle we'll talk about in a second. And then we'll have a few different 4 cycles in the Mandelbrot set as well that have a attracting 4 cycle. Again, anywhere in the hyperbolic component, the attracting 4 cycle can be associated to a derivative that's just in modulus less than 1 somewhere. This one is called the Airbus, I guess. This one is called the Cocopelli, and this one is the Cocopelli. So if you're like, oh, English isn't the first language or something that I've learned, like, is that a word? Like, I don't think so. Like, I think it's like a Southwest Native American fertility god, I think. But I think John Milner thought the Julia set kind of looked like it. I don't know. Right, so we have all of our different hyperbolic components, and if we look at our 3 cycles, like I just said, we have the airplane that lives here, and we have the rabbit, and we have the co-rabbit. And a good way for us to be in the Mandelbrot set is if our critical point is exactly in a 3 cycle. Because if you're in a 3 cycle, that's a good way for our critical point not to shoot off to infinity. So what we're noticing here is that there's 3 different ways that we can be in a 3 cycle. Either our 3 cycle maps like this, or it maps like that, or it maps like that. Okay? So but the point is that this is what I'm highlighting in green right here. Even if we took a point that's outside of the Mandelbrot set, it still has 3 cycles. They're just not attracting 3 cycles. So like the derivative along that 3 cycle is just a number that's bigger than 1 in norm. Okay? And so we can follow all of these guys together, and we can ask a very natural question: what is the behavior of a period p cycle, or a point, as we move around within our family of polynomials or rational maps or whatever? And we saw here that if we moved this cycle right here, maybe we moved it closer to here, this pink 3 cycle will converge to something that looks like that 3 cycle, and it'll happen to take on a criticality to it. But if we move this 3 cycle over here, it'll take on a different kind of 3 cycle. Okay? So the question that we're asking is just what's the behaviors that we can look at all of our different 3 cycles, or p cycles for any p bigger than 1. And just for clarification, when I say p cycle, I mean exact period. I don't mean like if you're p over 2, you'll return to yourself in p steps, but that's kind of like reducible. We don't want to care about that case. You want to ask what are the behaviors of our period p points? You can either ask 2 questions about just tracking the points or the cycle, right? So the cycle contains p points in it. So you can either ask, can we track a particular point, how that moves? Or you can ask, can we track about how the whole cycle moves together? So as just we're flying around somehow in our moduli space, we want to ask ourselves, what happens to our Julia set as we move around? The first kind of consideration that people noticed early on was that if we go on a loop outside of the Mandelbrot set, then if you follow this particular periodic point, as I do a loop starting from theta equals 0, and I go all the way around, so here's at theta 1/2, this point is now moved to this point, and then if I go from this to here, this point doesn't go back to itself, it goes back here. So in other words, if we just did one loop, our periodic points and our periodic cycles don't stay put. There's some amount of monodromy that happens as we go around in the Mandelbrot set, where points map to other points, and then there's a z mod 2z action to this, where it takes two loops around the Mandelbrot set in order for a periodic point or a periodic cycle to return to itself. So this is saying that if we wanted to follow around periodic cycles or periodic points, you would have to at least keep this information in order. And essentially why this is happening is this idea about we can keep this track in terms of something called the needing data. And I don't want to get too in depth about what the needing data explicitly is, but basically there's 2 points of canonical information to any oops, I do not know, it just happened there. There's 2 pieces of information that you can keep track of when you're looking at a point, a polynomial in your moduli space. One of them is what's called a characteristic angle. Characteristic angle. And this is an angle that lands at the critical value of our Julia set in the dynamical plane. So for instance, for this is a coarse approximation to what the Julia set looks like for the Kokopelli-4 cycle. And one critical value, we can call this an angle that is going to be expressed when we write it in binary. So this angle is 3/15, because under angle doubling, 3/15, this is a 4 cycle, 3/15 maps to 6/15, to 12/15, to 24/15, which is congruent to 9/15, and then this maps to 18/15, which is congruent to 3/15. So this guy really mapped back to where we began. And if we have this angle, this partition that we can generate when we try to define a needing sequence, is that we look at theta over 2, and then we take a preimage theta plus 1/2, and then we look at this partition of the plane, where we label every itinerary that lives over here with a 1, and every itinerary of every point that lives over here with a 0. So if we're looking at the itinerary of our critical values, it starts with a 1, then it goes to a 1, it goes to a 0, and then in this needing sequence, it would go back to a 0 right here. Okay? So it's just like an itinerary that we can make. And if we followed around, what happens as we look for a point that's outside of the Mandelbrot set, what happens to this sector, this line that cuts through our plane, is that because we're doing theta over 2, it's only making 1/2 twist as we do 1 whole twist of thetas as we go from 0 to 1. So this is saying that if we looked at the needing data of a periodic point, it'll bit flip. All of your 0s will become 1s, and your 1s will become 0s. So this is just a combinatorial or symbolic way that you can understand the monodromy. And so just to go back a second, our question was, what was the behavior of a periodic p point or a cycle in the Mandelbrot set? And there's really 2 different kinds of hyperbolic components in the Mandelbrot set that we can understand this as. There's primitive, which people like Miguel or Luna or Claudia know a lot about in terms of parabolic theory, parabolic implosion and all of this. And what's happening is that around a cusp that you see in the Mandelbrot set, like say near this 3 cycle, the airplane, if I take a nearby parameter, maybe it's slightly outside the Mandelbrot set, maybe it's in the Mandelbrot set as long as it's nearby, what's happened is that I'm going to have 2 periodic 3 points that are getting very, very close to each other, but they're not actually touching yet. But as soon as I get exactly to the airplane's root of its hyperbolic component, these 2 periodic 3 points actually collide. And they become the same point, but now it has a periodic 3 cycle with like higher multiplicity. because there's multiple 3 cycles that are acting along the same literal 3 points. So what's happening here is that we can define a primitive polynomial or a primitive hyperbolic component is what happens when you have 2 different p cycles that collide together. And then this is exactly like this riddle that we had at the beginning of the talk, is that one of them is a $20 bill and the other one is a $2 bill. And you can exchange them as you go around. Because if one of them, if you're saying that as you collide, one of them isn't given by the combinatorics of like 0, 1, 1 or some other binary expansion, bless you, you can say, well, the other one is given by a different cycle. But you can contrast this, what happens in the satellite case. When you're looking in the satellite case, is that nearby this root of the hyperbolic component of the rabbit, you're still going to have a periodic 3 cycle, but it's not colliding with any other 3 cycle. It's colliding with itself. Okay? So nearby, you're going to have these 3 points, which are in a cycle. We can witness this by seeing under angle doubling, the point of 0, 0, 1 maps to 0, 1, 0, because it's just rotating your primitive 3 angle, and then that rotates to 1, 0, 0, which maps back to 0, 0, 1. Contrast that to this airplane case over here. The points that we had were labeled by 0, 1, 1, and no matter how many times you rotate that, you're still going to have 2 1s adjacent, but for the 1, 0, 0, you're only ever going to have 1 single 1 in there. So this is like a combinatorial way you can see that neither of these 2 points are in the same 3 cycle, but what happens near the rabbit is that you have a single 3 cycle that collides with itself. So we can call this either a degenerate collision, where a single cycle collides with itself, or you can understand it by saying, and this is related to why in the geometry of the Mandelbrot set, we have this hyperbolic component touching this other hyperbolic component up there. We see this as well when we look near this cusp, this big cusp of the Mandelbrot set, is that what's happening here is that we have 2 fixed points that are colliding together. And again, near the root of the basilica, we're going to have a 2 cycle that collides with itself. So this, again, would be an example of a primitive, and this one right here would be something that would be satellite. And the point is that the satellite ones don't have any monodromy when you go around. If we started at a primitive guy, and the blue was on top and the pink was on bottom, as we did a loop, our labelings of our 2 different points would change so that the blue and the pink would be interchanged. But if we started with the satellite guys, there's only 1 cycle that can only permute with itself, so the cycle stays fixed, but you would have monodromy if you looked at if you're marking the different point. So a different point goes to a different point in the same cycle, but the cycle itself is preserved. Okay. And so again, the question was asking, how do we look at what the behavior is as if we follow around a point or a cycle? As we can see, if we're following around a cycle, we'll pick up different information than if we just follow around a point. Because if we follow around the point, we'll have monodromy around satellites, but if we follow around the cycle, we will not have monodromy around those points. So this way, we can get associated curves of families of moduli spaces. And this is called, the first one is called the DinAmicI curve over a family. This F1 is our family of quadratic polynomials for right now. And this is saying that you're taking a parameter that lives in pure 1, 0, the polynomials, but then you're also taking a period p point for the polynomial fc of z. And you can realize this algebraically. If you have a root of the polynomial fc to the p is equal to z, this is saying that if you iterate a point p times, it'll come back to itself, because z will equal to fp to the z. And this fancy notation up here just means you don't do it in p over 2 steps or p over 3 steps or whatever. So this is what happens when we follow around a point. We'll get these DinAmicI curves, but if we get this curve down here, this is called the marked cycle curve, because right now we're not following around just a point, we're following around the entire cycle. So it means that we're marking the whole cycle, not just the point. And we can also specify this algebraically by something called the resultant, which is just a fancy algebraic way of saying like an intersection of 2 different conditions that are happening, where we need it to be that if you're going to mark a whole cycle, you certainly need to have it work for every point in the cycle. So that's why you want to intersect this condition with also some polynomial condition that uniquely is invariant on your p cycle. And then we can just note that there is a pretty immediate relationship with these two different curves, is that because the p cycles are invariant, a point is in a p cycle, that you have a z mod pz symmetry from this curve up here, the dynatomic curve, over the marked cycle curve, just by taking the relationship of c comma z maps to c comma f of z. Because for the same map c, f of c, then z and f of z and f of z and all of your p iterates are in the same periodic cycle. Okay, but enough algebra. You guys came for the pictures, I guess, not for the words. But before we get to the picture, sorry, I forgot about this slide. Actually, I'll come back to that slide in just one sec. So when we look at these pictures, what's happening is that we have our base curve down here. And to get the marked cycle curve, we're marking all of, this would be for p equals 1. And at p equals 1, p equals 1 just means a fixed point. So this means we're marking two of our fixed points. For a polynomial, we have two bounded fixed points. And the cusp that happens at the root of the main cardioid happens when we cannot disambiguate the two different fixed points because they hit the same parabolic fixed point in the dynamical plane right there. But we record this in the marked cycle curve. This point right here would be the lift of this center point right here, but marked of one fixed point. But you have a second fixed point as well, so we would have a second lift of the same center of our main cardioid, marking our second other fixed point. Okay, so for every fixed point you have, you will get an associated lift of each component in the Mandelbrot set. So for instance, this is the basilica marked with one of your fixed points, and this is the basilica marked with the other one of your fixed points. And we said that the dynatomic curve was going to be a z mod pz cover of a marked cycle curve. In this case, p is equal to 1, so it's just an isomorphism, and our dynatomic curve is the same as our marked cycle curve. When we look at p equals 2, there's only one component of the Mandelbrot set that actually has p cycles. And it's what we saw earlier, that it's a satellite curve, so it has the single 2 cycle collides with itself. So this means when we're marking the level of cycles, it's not actually permuting the cycle as we go in a small loop around our basilica's root. So it doesn't actually change anything when we looked at the marked cycle curve. But if we look at the dynatomic curve, which records the monodromy of particular periodic 2 points, in that case, when we go around, the 2 points get exchanged. So we do pick up on monodromy on the level of points, but not on cycles when we look at the dynatomic curve. And I drew in red how we can see this as a 2-to-1 cover of the Mandelbrot set over here, where you can see it's kind of an exercise in seeing creatively where we'll have this main cardioid, and then you can see that it sort of continues this way, and then that is the sort of twisted version of the Mandelbrot set, if that sort of makes sense. For higher examples, we get a bit more interesting looking curves. Again, our base space is still going to be the Mandelbrot set, but if we mark a 3 cycle, now we have 3 different components in the Mandelbrot set. We have the airplane, the rabbit, and the co-rabbit. Both of these guys were satellite, right? So this just meant that you had 2 3 cycles colliding with them. This was a 3 cycle colliding with itself. This was a different 3 cycle colliding with itself. So there's no cycle monodromy there. The only place that we have cycle monodromy is when we look around the root of a primitive component at the airplane when we had 2 different 3 cycles colliding with themselves. So what we're seeing when we look at the marked cycle curve is that we see one Mandelbrot set that corresponds to marking one of those 3 cycles, and it ramifies at the point at which both of those 3 cycles collide at the root of the primitive airplane component. And then we have the other Mandelbrot set, which is the lift of the other 3 cycle. When we look at the dynatomic curve, which is a z mod 3z cover of this, you can see that we'll have, now we have to keep into account the monodromy of the points around the rabbit and the co-rabbit. And then this is why, again, the rabbit and the co-rabbit were in red right here. That's why you can sort of see this is a really distorted copy of the Mandelbrot set right here. We have a Mandelbrot set, and then here's its rabbit. And then it'll go over here, which is the copy of the cycle 3 curve. And then this is 1 component, 2 component, and 3 components of this z mod 3z lift. And Right. So that's if we mark a p equals 3 cycle, there's only one point that it ramifies over. If we mark our p equals 4 cycles, what we drew here, we had the Airbus as primitive, the Kokopelli is primitive, and the Co-Kokopelli is all primitive. So we'll have 3 different ways that 2 different 4 cycles can collide together that we would have to record about how to disambiguate when we look in a cover. And this is what we see right here, where this component and this Mandelbrot set and this Mandelbrot set get married over this point, which is the Kokopellis, and then this one is the Kokopellis of each, and then this one where they meet is over the Airbus of each one of them. Now, if you guys have heard of the Mandelbrot set and you guys have heard of manifolds, I like to call these guys mandolfolds because they're locally the Mandelbrot set. But in general, when you look at them, they can be higher genus. If we looked at the marked p cycle curve for p bigger than 4, then you're going to get something that's genus which is bigger than 2. So something is going to get really weird. These guys are going to be high degree mandolfold Riemann surface guys really quickly. Yeah. Mm-hmm. Oh.
The pink point in the cycle 3, there.
Right here?
Next to in the next one, there.
Mm-hmm.
The pink point is the root of the airplane.
Yeah, this is the root of the airplane's hyperbolic component. Because at this pink point right here, which is the associated to the root of the airplane component right here, you'll have 3 different 3 cycles that are colliding together. So this is giving you a ramification point in your marked cycle curve because it can't disambiguate the 2 right there. Right, yeah. Cool. And then just to put this in a little bit more of a particular context, so when we defined this earlier, we said define this algebraically, you would define the marked cycle curve as the resultant of your diatomic polynomial and just any polynomial that's invariant on our p cycles. The most dynamically natural one to do is exactly this multiplier function that parameterizes the hyperbolic components that contain your p cycle. And if you look at what this curve is, this is the natural domain of the multiplier function. But according to the primitive components, which have a cusp here, your multiplier function is going to have a singularity when you look in the curve. But when you resolve that singularity by applying finite limit blowups, then you're going to actually get your marked cycle curve. So the marked cycle curve is the smooth curve that is the natural domain of your multiplier function. And then this is this picture of what the marked cycle curve of period 3 looks like over the family of quadratic polynomials. And what you're looking at is you're looking at the contours of your multiplier function. So you can see that it has zeros at when you have an exact critical point in a 3 cycle, which is here, here, and here. And then, for instance, this one is when the 3 cycle of the airplane is in it has a critical point in it, but then your airplane has a second 3 cycle as well that's not in a critical 3 cycle, and that one will have some multiplier that it's bigger than 1. And there's a lot of open questions just about this curve and what this looks like. For instance, you can see that you'll have lots of critical points of your multiplier function, like for instance right here where you see these like lemniscate crossings. And in general, this is like very poorly understood, that people really don't understand this at all, about what this looks like or how they distribute when p gets higher. Okay. So just a brief history about a lot of these things. These diatomic curves are really well understood. And if I just go back one second. So if our diatomic curves, these were this was this z mod pz action over our marked cycle curve, and then this was a projection down to our base space. These diatomic curves are very well understood, and this is a very dynamically natural curve as well that defines your multiplier function that is birational to our marked cycle curve. So basically in the history is that over the family of quadratic polynomials, the diatomic curves are very well understood. But it seems like these marked cycle curves appear to be new, and it seems like nothing else has really been studied over any holomorphic family of functions besides quadratic polynomials. So that's, I guess, the summary of the history that we'll see right here. And before I state the main theorem, I want to quickly identify a little bit of notation. If you're more familiar with combinatorics, these are also known as Linden words, and these also count the number of degree P polynomials over the finite field F2. But basically what we're looking at, what we're going to call CP, is that these are all of our strings of zeros and ones, which are not reducible to a smaller chunk. So for instance, 0, 1, 0, 1 does not count in the set C4 because 0, 1, 0, 1 is just 0, 1 repeated twice. And then you're allowed to take all of the rotations of this. So 0, 0, 1 is in the same cycle class as 0, 1, 1, 0, is in the same as 0, 1, 0, 0, is the same as 1, 0, 0. Okay, so this is some set CP. And for instance, over p equals 4, we'll have 4 different classes. We'll have 0, 0, 1, and 1, 1, 0. And that we're going to notate these by having a complex conjugate over them, or a conjugate over them, because this is related by bit flip. Right? If we change all the zeros to ones and the ones to zeros, you're going to go from A to A bar. But sometimes you'll have special ones like B right here, which is 0, 0, 1, 1, which when you do the bit flip, it gives you another guy in the rotation class. Okay, so these ones we can call these guys ramified. And then we're going to call CP bar, which is just all of the CPs modulo bit flip. So in this case, now A and A bar are going to be in the same class of CP bar, but they were different in CP. And anything that was the same, so if B was equal to B bar already, those are still the same in CP bar. OK, so remember, all of this was just trying to explain these pictures that we're seeing right here. The main theorem that we had, and this was joint with Mala, Danny Stoll, and Giulio Tiozzo, is that the Marx cycle curve has a canonical and explicit cell structure that we can give to it, which is a lift of a very particular tree in the Mandelbrot set, such that we can very explicitly tell you what its vertices, edges, and face are. So if we're saying that the vertices, well, by definition, all of the vertices are lifts of our center polynomial z squared. So what this means is that we have to specify an additional period p cycle. These period p cycles can be labeled by elements of CP. So all of our vertices are in canonical bijection with elements of CP. All of our edges in our cell structure are going to be lifts of the path from a particular p cycle. For instance, this is the path between the Airbus and z squared. And we understand that these branch exactly over the primitive components of period p in the Mandelbrot set. This is what we saw when we saw that there was a local monodromy around the cusps of our primitive components. And so in that sense, that the edges correspond to the primitive components in the Mandelbrot set. So if we look here in this Marx cycle 4, the Airbus is right here. And if we follow the lift of the vertex z squared marked with the cycle 1, 0, 0, 0, it ramifies at the Airbus with also the cycle z squared marked at 0, 1, 1, 1. So we get an edge in our cell complex that corresponds to the polynomial of the Airbus. And then finally, for the reason that we talked about at the very beginning about how the kneading we had monodromy as we went around in the Mandelbrot set, that faces then correspond to elements of CP bar, and also explicitly in the sense that the matching local degrees, so if we look at our projection map, if we look in a little loop around here, we'll see one cusp of the Mandelbrot set. So this only has degree 1 mapping onto here. This is kind of like an outside-in version of the Mandelbrot set on the interior face right here. But on the outside face that we'll see one cusp, we'll go around, we'll see another cusp up here, and we'll go around. So this is a 2-to-1 lift of the pier 1, 0 downstairs, which is reflected in the fact that 0, 1, 1, 1, it has a non-ramified bit flip to 1, 0, 0, 0, which is a different cycle class than 0, 1, 1, 1. And the point is that we can get this for any p, even the ones that are high genus, is that we can draw an explicit polygonal cell decomposition. And we can compute things like its genus, and here's what it's stated as just for primes. So it's just a very concrete way that we can understand and draw these pictures. To give you some idea about what the proof looks like is that if we focus ourselves around a particular edge, which is based at a polynomial, is every edge we saw corresponded to some primitive p cycle in the Mandelbrot set. There's 2 pieces of canonical combinatorial data that we can look at. We can look at characteristic angles, which were the angles that landed at the root of the periodic component in the complement of the Mandelbrot set. And then we can also look at the needing sequence of the polynomial. And the reason that there are two of these is that we have two different angles that land at the root of our hyperbolic component. In the dynamical plane, that this translates that this lands at the root of the critical value phi2 component, and this defines a needing sequence partition. But we just as easily could have taken another critical value, the second one that also lands here, and then this would also define a partition element of the to define needing sequence as. So this is to say is that we have two different strings that could count as the needing sequence for a primitive polynomial. If we use this other partition, we would see that this would read 1, 1, 0, and, oh, sorry, this was supposed to go up here, and then this would be 1, 1, 0, 1, 1, 0, 1. So we could have two different labelings because according to this partition, our fourth post-critical point is labeled by a 1. And the proposition is that so we have two different characteristic angles that specify our hyperbolic component. And when we look at these in binary and interpret these as words in CP, this defines when we have an edge that has the vertices given by its two different characteristic angles. So if we started with an edge right here that corresponds to a polynomial that's primitive, it has two different characteristic angles that are in two different periodic P cycles, and its vertices are the CP element that corresponds to each one of those. On the other hand, we have two different needing sequences that we can give to any quadratic polynomial, and this allows us to define the two different faces that it's on by looking at the bit flip class of the binary word of the needing sequence of each one that is permissible. And we can use these to define two different algorithms to define it. Let's see, I only have a couple minutes left, so I wanted to not start with the telephone algorithm, but I want to start with the bar method. It was that we had these vertex relations, and we also had these face relations. Julio, Danny, Mala, and I worked this out in Berkeley when we were at this conference at MSRI, and Yasmin was there, and she was doing this workout regimen to actually stay in shape rather than just eat sliver pizza all day like the rest of us. And it was at this place called the bar method. And this turned out to be just what we were also calling our algorithm. So this algorithm kind of became dedicated to our second Italian in this talk. And the way that this algorithm works to determine our cell structure is that you start with all of your primitive P cycles in the Mandelbrot set. So this is being done for P equals 5. Okay, so we have 15 different 5 cycles somewhere in the Mandelbrot set. These guys, unfortunately, don't have cute names like the airplane, basilica, the rabbit, or whatever. I like to call 3/31 the giraffe or the llama, but that really hasn't caught on yet. But each one of these has a needing sequence, and I'm labeling it like by some number like 1 or 0, and then the last entry being a star to reflect that it really can take on a 0 or a 1, depending on which of our two partitions that we chose to take. So we gather all of our needing sequences, and then by taking one of our two partitions, we'll get two binary strings that either end with a 0 or a 1. So now each polynomial has two different binary sequences associated to this. We can interpret these binary elements as elements of CP. So in CP, where P equals 5, we have 6 different classes, and there's A bar, there's B bar, and there's C, and there's C bar. And I'm not going to tell you exactly how I chose them. It'd be a little bit too cumbersome. But you don't have any faces that are self-conjugate. And this turns out to be because 5 is an odd number. So we have this then picture of the Mandelbrot set with each polynomial associated to some element of CP. And the way that we get our face relations is what we call the bar method. And what we do is that we list all of the maps. If we want to get the face that corresponds to A or equivalently to A bar, we choose all of our polynomials that have an A or an A bar labeling. Let's just start with, I guess, A. There's only one polynomial that has an A labeling, which is 15 over 31. There's no one else that has an A. So now we go to the A bar, and we list all of the elements in order that have an A bar. So first we have 3 over 31. So this is going to be another edge. 5 over 31, which will be another edge. 13 over 31. 26 over 31, and then 28 over 31. And this turns out to be the way that we can understand what edges bound a particular face. There quickly is another algorithm that we can do to get specifically the edge relations, or the vertex relations, by saying just essentially based on when you look at your characteristic angle, what are the two different elements of CP that represent the characteristic angles that collide at a particular primitive element. And doing a similar process, this gives us which two edges have to bound a particular face. And when we apply both algorithms together, this gives us our complete labels where we understand both the vertex labelings and the face labelings. We can similarly do things over Pier 2, but I didn't really budget my time very well. So I'm going to stop there. But thank you.